Hi, this is Amelia McCutcheon from the Zen of Chemistry. This video is about qualitative spectroscopy and spectrometry. In particular, we're looking at infrared spectroscopy, NMR spectroscopy, and mass spectroscopy. So let's look at spectroscopy and what that actually is. It is the interaction of light with matter. So that light can affect either the molecules, the electrons, or the nucleus. The nature of the interaction is dependent on the energy of light. Okay, so if we look at this equation here, I've popped this mostly here for the physics students. Okay, energy is proportional to frequency and it's inversely proportional to wavelength. Okay, so depending on the wavelength will have a particular energy, which will have a particular type of interaction with matter. And the way we use this in spectroscopy is it provides us information about molecules. So again, the three I'm looking at today are IR, NMR, and mass spec, and I'm looking at them from the perspective of qualitative analysis, which is trying to work out what a molecule looks like. Okay, so you can see here IR and NMR essentially are qualitative techniques. You can use mass spectroscopy as a quantitative technique, but I'm not going to be covering that in this video. They are generally three techniques that we use for hydrocarbons, and again for mass spec you can have much wider uses for mass spec, but essentially we're going to be looking at analysing hydrocarbons. Infrared spectroscopy and NMR, okay, they affect the molecules quite differently. So infrared light is used in infrared spectroscopy and it causes absorption of light, causes the bonds within the molecule to vibrate. Okay, and we'll talk a little bit more about that shortly. NMR, actually, we use radio waves for NMR, and that actually causes NMR active nuclei to change their spin. Okay, and that spin can be detected and then used to determine some information about our hydrocarbon molecules. I've got mass spectroscopy. It's got a slightly different table here because it's actually not a spectroscopic technique, it's a spectrometric technique. And rather than shine light on our molecules, we actually bombard our analyte with high energy electrons, and that causes essentially fragmentation of our molecules, which can tell us a bit more about our molecules. These three are generally used in conjunction with each other, and they all give us a different type of information that we can use as a toolkit to actually analyze unknown molecules. So let's get into it. Infrared spectroscopy. Infrared light causes bonds in molecules to move, okay, and they vibrate. So they can stretch, they can bend, they can wag, they can twist, they can rock, depending on whatever wavelength you're referring to. So at this point in time, I'd refer you to your data book. If you're a VCE student, you'll have a data book. If you're an IB student, you'll have a data book. If you're a university level student, you may have to go and actually look in the textbook that you've got. There should be some information on this somewhere. There'll be a table essentially that refers you to particular wavelengths having particular effects or particular absorbances for different functional groups. So the example I've got here is aspirin. Okay, now you'll see lots of little notes here. This is an aspirin molecule that I made, and so here's aspirin here. Okay, and you'll see all different kinds of notes here, but what I really want you to take away from this, without looking at those notes, you can see here are our peaks. You'll notice that in comparison to other techniques, the peaks are actually upside down, if you like. So we look at not absorbance but transmittance. Down the bottom here we've got wave number. So we go anywhere from, it's usually about 300 up to about 4,000 wave numbers. Now you'll notice that this area here is actually quite messy. This is what we call the fingerprint region. okay? And the fingerprint region is essentially like a fingerprint for that molecule. It's very specific to each molecule, so you know, you'll see there are a few little notes I've taken here, but I haven't gone and labelled each and every peak, essentially because the fingerprint region is quite difficult to analyse. So we do leave that for the pros to do. For the purposes of basic level qualitative chemistry, there's a few that I'd like to point out in particular. So the OH stretch here, the OH here, that's our OH there, so it's only a little peak. Okay, the OH stretch is usually quite a broad peak. It can be actually quite large, so you can actually see sometimes that it's quite a large broad peak. And when I say broad, I mean wide at the base. Okay, as compared to some of these peaks, you can see their bases are quite narrow. So that's our OH stretch. The other one I really want to point out is our C double bond O stretch. Okay, so that's the C double bond O there. And I've put CO2. Sometimes if you've got a molecule and you're analysing, you're not expecting to see a C double bond O in there, sometimes it can be due to carbon dioxide. So it's not CO2, it's a C double bond O, or carbonyl stretch. I've picked out a few others there. I'm not going to focus in on them today, but definitely if you've got an infrared spectrum and you have a look at your table and you know or maybe not know what your molecule is, you can match up those wave numbers to particular parts of your molecule. That's essentially where I'm going to leave infrared spectroscopy for the purposes of this video. If you're studying VCE chemistry or IB chemistry, the amount you're going to need to deduce from an infrared spectrum is going to be quite little. Okay, so just really focus in on looking for obvious trends and then move on from that infrared spectrum to something like NMR. So NMR stands for Nuclear Magnetic Resonance Spectroscopy. It's an extremely powerful technique. I know people who can use this technique alone without using anything else to work out the entire structure of complex molecules. Okay, the way it works is radio waves are shone onto your sample, and what they do is they cause NMR active nuclei to change their spin. And when I say NMR active nuclei, they are particular types of atoms that are able to absorb NMR, or able to absorb radio waves and hence change their spin. So not every atom is NMR active. The ones we're looking at in this scenario is HNMR, so proton NMR, hydrogen NMR. Okay, so it's the isotope 1 hydrogen. And then we're also looking at carbon-13, so not the most abundant carbon isotope carbon-12. We're actually looking at carbon-13 NMR. Carbon-12 is not an active NMR active nuclei, whereas carbon-13 is. So essentially the way we calibrate it is we use this thing called tetramethylsilane. So we'll put that in with our sample, and it's our reference chemical that we essentially, when we're putting our sample into the NMR, we find where that TMS signal is and we set that at 0, and then everything within our molecule is going to be in reference to or relative to that TMS signal at 0. Now, the most important thing you need to know to begin with is how to read NMR spectra. And there are 3 pieces of information on an NMR spectrum. There is the chemical shift, which is essentially the position of the peaks on the x-axis. So it'll look a little bit like an XY graph, kind of. So position of the peaks on the x-axis. We've got our splitting. So we can have low resolution and high resolution NMR spectra. Mostly you'll come across high resolution, and where we have a group of peaks, they can be split into a number of peaks. And the third piece of information is integration, and that relates to how many protons or how many carbons are associated with that peak. Okay, so I'm going to start with proton NMR. So if you're studying VCE chemistry, you'll see that in the data book pages 5 to 7 is your NMR chemical shifts. You can draw on, and what I like to do when I'm introducing NMR to students is that I get them to draw their own NMRs. Okay, if you can draw them, you can actually read them. Okay, so you'll notice here's our TMS signal at 0. Okay, whatever peaks we put on here, you'll notice it kind of goes the other way. We'd normally have -1, -2, -3. I don't know why this is. It's just essentially the convention in NMR. We've got our chemical shift from 0 to 10. There are some that can go up to about 12 or 13, but for the purposes of what we're going to do today, it's going to be from 0 to 10. So that's our chemical shift, our x-axis, and that's measured in ppm. The example I'm going to use for the purposes of this video is ethanol. So what we need to recognize in ethanol is that we have 6 protons in our ethanol in 3 different chemical conditions. Okay, so you'll notice I've got the red OH. Okay, when I say different chemical conditions, they're essentially close to or further away from different types of elements. In this case, it's going to be oxygen. So in this case, hydrogen here is right next to that oxygen. So that's one chemical condition. The second chemical condition is from that oxygen there, these 2 hydrogens are 1 step away from that oxygen, and so they're in the same chemical condition. And then this group of hydrogen atoms are 2 steps away from that oxygen there. Okay, and so the ones that are in the same colours, they are essentially equal to each other because they are the same distance away from that oxygen there. So that's the first thing we need to look at. So we're going to have 3 groups of peaks. Those groups of peaks are then split. So the groups of peaks is kind of like our low resolution NMR. The groups of peaks are then split by hydrogens that are adjacent or next door to each other. So in the case of these 3 hydrogens, they are next door to 2 hydrogens. And we use this thing called J3 coupling. It has to be able to go through 3 bonds. So from this hydrogen here, we can go 1, 2, 3 bonds. So that hydrogen there and that hydrogen there can talk to each other. That's kind of how it works. They affect each other. We can't have this hydrogen affect or talk to through 1, 2, 3, 4 bonds to this hydrogen here. Okay, so these 3 hydrogens can talk to these 2 hydrogens, and we use this thing called the N+1 rule. So next door to these 3 hydrogens here is 2. So 2 plus 1 will give us 3 peaks for these 3 hydrogens. For these 2 hydrogens, next door is 1, 2, 3 hydrogens. There is a 4th over here, but this oxygen kind of acts as a great big brick wall between this hydrogen and this hydrogen. So even though there's 1, 2, 3 bonds between the red and the green hydrogens, okay, or these 2 hydrogens here, because of this oxygen, it shields or makes sure that these hydrogens can't talk to each other. Okay, so next door this hydrogen can't see this hydrogen here, but these 2 hydrogens can talk to or are split by these 3 hydrogens here. So 3 plus 1 is 4 peaks. Okay, this hydrogen over here, it's all by its lonesome. It can't talk to any other hydrogens nearby because of our oxygen brick wall here. Okay, so 0 are next door. 0 plus 1 is just a singular peak. Okay, so I've got down here shielding okay, the oxygen is essentially acting as a great big shield or a brick wall, not allowing those hydrogens to talk to each other. So now we've got our, what we call our triplet, our quartet, and our singlet peaks. What we need to do there now is to have a look at where they go onto our NMR spectrum. So we'll start with our 3 hydrogens over here. If you go and have a look at your data book, whatever data book you have available to you, you'll have a look and see that CH3 molecules by themselves relatively far away from any electronegative atoms, oxygen, nitrogen, chlorine, that kind of thing. They live in the vicinity of about 1 chemical shift. So I'm going to put my triplet, remember, that's split by 2, 2 plus 1 is 3, and then because it's a fair way away from that OH, it's going to go at about the 1. The CH2 here, okay, remember that was a quartet or 4 peaks, okay. If you have a look at the data book, you'll find that when two hydrogens are next to an OH, okay, they can be in a range. I think it's from about 1 to 6. Okay, so I'm going to put them about 4. I'm working from my memory here, so I might be telling you the wrong thing about the numbers, but definitely within that range there. And then our OH, our singlet, our single peak from our OH, if you look that up, you'll find that that can be anywhere in a range, but I've chosen to put it at 6. Now, let's look at our integration. For those of you who are maths method students or algebraic type students, if you've done integrals, here's our real life example. It measures the area under the peak, and the area under the peak tells us how many hydrogens are associated with a group of peaks. Okay, and it's usually shown as an S shape. Okay, so if we go to our peaks here, okay, our first one, here's our S shape here. Okay, we've got 3H, so we can say, all right, this group of peaks is due to 3 hydrogens, 1, 2, 3. This one here, you'll see it's about 2/3 the height of this one here. So that's about 2H due to 2 hydrogens. And then our last one, compared to the first one, its height is about 1/3 of the height. So we give that a 1H. It's due to our only 1 hydrogen here. So that's how you construct an NMR spectrum. I recommend you go and do a few of these and then move on to actually reading an NMR spectrum. For carbon NMR, we're looking at carbon 13, which is NMR active, but carbon 12 is not. What you've got to keep in mind is that carbon 13 is only in a 1% abundance in the world. Okay, so the peaks are relatively a lot smaller, and carbon NMR takes a lot longer than proton NMR. Carbon 13 NMR is essentially used to identify different carbon atom environments. Depending on the different type of carbon NMR you do, or depending on whether you've got splitting, all sorts of things, it's actually much more complicated than proton NMR in the grand scheme of things, but for the purposes of basic spectroscopy, it will be talking about carbon environments. So for the purposes of VCE chemistry, all you really need to deduce from a carbon NMR is how many carbon environments do you have, and according to their chemical shift, you can get some idea of what that's from. So if we now look at, again, we'll use our ethanol as our example. Here's our TMS peak, again at 0. You'll notice that the chemical shift for proton NMR, remember, was 0 to 12. So for carbon NMR, it goes from 0 to 200. The scale is actually quite different in carbon NMR. So if you don't have a label for your NMR, you're not sure if it's a hydrogen or a carbon, that's always your telltale sign, is the scale along the bottom there. So we've got two carbon environments for this particular molecule. We've got this one here and this one here. This one's close to the oxygen, whereas the purple one is a little bit further away from that oxygen. So if you go and have a look at your carbon NMR table in your data book, a CH3 can be in, I think it's like 18 to 40. I can't remember the numbers exactly, but 20 will do for today. And then a carbon that's right next to an alcohol group here is going to, I'm going to pop it at 60 ppm. Okay, so if you saw this without any information at the top here, if you just saw two peaks, what you get from that is that there are two carbon environments, and from the chemical shift you may be able to deduce exactly where that comes from. Sometimes that's not a telltale sign, so you know, if you've got a range of your chemical shift, they can often be anywhere in that range depending on the molecule. So now we'll move on to mass spectrometry. Okay, lucky last one. This video is going to be a bit longer, so I do apologise. This can I try to keep my videos 15 to 18 minutes, but this one's going to be a bit longer today. Mass spectrometry is a technique where molecules are bombarded with high energy electrons, which causes the molecule to ionize and then break up into smaller pieces, usually. The ions are then subjected to a magnetic field which causes them to accelerate and bend according to their mass to charge ratio. And we use this interchangeably mostly. These two forms here, M for mass /E or M/Z, which is indicative of our mass to charge ratio. For the purposes of basic mass spectrometry, you can really think of the mass to charge ratio as being indicative of molar mass. Okay. Then the detector measures the current due to those ions going through the detector, and we record the data as what's called a mass spectrum. So here's a chemical equation for the ionization. It's just a representation of what happens in ionization. So we've got our uncharged molecule here. It's being bombarded with high energy electrons. When those high energy electrons smash into our molecule, okay, that the incident, or the electron that's being shot at our molecule, is going to be ejected from the molecule, but it's also going to take another electron with it. So we are left with a molecular ion, or a parent molecular ion. So it's essentially our molecule minus one electron. And so that's going to be positively charged. And then what we've got is our two electrons. So the incident electron plus the electron that's been ripped off this molecule here. Okay. So from there, our molecular ion, depending on how much force or how much energy that incident bombarded electron has, will determine on how stable that molecular ion is, and also really it's just reliant on what that molecule actually is. So sometimes that parent molecular ion can be quite stable, but in most cases it won't be stable, and it will want to break apart into smaller pieces. One part will retain the electron and become an uncharged free radical. So that's how we denote this dot here. That's a free radical. And the other will be a positively charged ion. Okay, so the parent molecular ion can actually, that electron can either go to the B part of our molecule, or it can go to our A part of our molecule. The mass spectrometer detector can only detect the ions and not the free radicals. Okay, and there's lots of different possibilities that can occur. This is quite a simplified thing, a simplified representation of what actually happens. So in the mass spectrometer detector, you'll be able to detect M+, A+, and B+, but not these free radicals. So here's our example. We've got ethanoic acid. Okay, our ethanoic acid is bombarded with high energy electrons. When that electron is ejected from our molecule and it takes another electron with it, we're left with this parent molecular ion, which is essentially our molecule minus an electron. Okay, it still has a mass to charge ratio of 60 grams per mole, or a molar mass. Okay, and that electron could be taken away from any of these bonds here. Okay, and depending on where that electron has been ejected from and how well that molecule can compensate for that, the molecule then breaks into pieces. So some of this whole molecule will reach the detector, but also there's going to be other molecules that fragment. Okay, so the molecule could actually fragment here, for example, okay, which gives us a mass, two fragments, one of mass charge of 1, because the molar mass of one hydrogen is 1. Or if you go and calculate the molar mass of all of this, we've got a mass to charge of 59. Okay, so 12 plus 1 plus 1 plus 12 plus 16 plus 16 plus 1 from our periodic table. The molecule could also break, say, here, giving us a peak of 15. 12 plus 1 plus 1 plus 1 is 15. And then the rest of that molecule is 45. The molecule could also break here, which gives us two fragments, one of 43 and one of 17. Okay, and it can also break at other points, but I'm just going to use those as examples. So if we now have a look at a mass spectrum for ethanoic acid, you can see up here is our parent molecular ion. Okay, at 60, because the molar mass of ethanoic acid is 60, there's our parent molecular ion. I just want to point out there's this peak here, which is our what we call our base peak. It is the most abundant fragment ion, and so you can see it's got a relative intensity of 100. So we scale all of these other peaks, or the abundance of those peaks, in relation to our base peak, which is 100, and then the rest, if they're less abundant, they're going to be smaller peaks. So just to point out some of these molecules here, so we've got our 45, which is our red one here. We've got our 15 down here, which is the other half of that 45. We've got a 43, which is this half here. But we don't have a 17. There's very little 17. Okay, so most likely what happens to that 17 is it breaks off. Okay, so once it's down to a 17, it'll probably fragment further. You'll notice that we don't have any 1s. Okay, so usually hydrogens don't reach the detector very easily. And then you'll also notice there's also not a 59. So that 59 fragment must be very unstable, so it doesn't even reach the detector, it further fragments into all of these different peaks here. Okay, so this example, you know, there's lots of other little peaks here. You generally don't need to look at all the tiny little peaks, but really we're looking at the major peaks here. You'll see the 15, you know, it's a smaller peak, but it's still, you can tell where it comes from. So essentially when you see a mass spectrum, you're expected to be able to look at it and take just bits and pieces from it that you need. The one thing I want to cover just before I finish this video is about isotopes. So if you consider, we've got carbon isotopes. Okay, so we've got 99 to 1%. So I'll just go back. People might say, oh, well, molar mass of this is 60, so why is there a peak at 61? Well, the peak at 61 is actually due to one of these carbons not being a carbon 12, but being a carbon 13. So that explains why that little peak is there. A carbon 13 is going to give you a molar mass of 61. So we've got carbon isotopes, we've got chlorine isotopes and we've got bromine isotopes, and they're all in, different relative abundances. So molecules with one or more atoms with isotopes will actually display mass spectra with peaks associated with these isotopes. So we generally, deal with the molar mass of different atoms. Okay, so we know that the molar mass of, say, chlorine is 35.45. Okay, but the reason why it's 35.45 is because it's a mix of chlorine 35 and chlorine 37. Okay, but in real life they don't weigh 35.45, they weigh 35 and 37. Okay, so we see mass spectra with peaks associated with these isotopes and in proportion to their relative abundance. So let's have a look at dichloromethane. Oh, no, sorry, this is chloromethane. Little typo, I apologise. CH3Cl. Sorry for the typo, guys. So this is chloromethane with a chlorine 35, and this is chloromethane with a chlorine 37. So this has a molar mass of 50. 12 plus 1 plus 1 plus 1 plus 35 is 50. And then this one has a molar mass of 52. So we'll see on our mass spectrum a peak at 50 and a peak at 52. Okay, and because of the relative abundances, 76% and 24%, the chlorine 35 peak is going to be about 3 times larger than the chlorine 37 peak. So the mass charge ratio 50 is going to be about 3 times the size of 52. So let's look at that mass spectrum. There's our 50, there's our 52, and because we have 75% of our chlorine 35, that makes that 50 peak quite large, and then our chlorine 37 is causing this 52 peak to be about a third of the size of this one here. Now we move on to dichloromethane. Okay, now we've got 2 chlorines on our methane molecule. So we could have a chlorine 35 and a chlorine 35. We could have one of each, 35 and 37, or we could have 2 chlorine 37s. And so the molar mass of dichloromethane is 84, 86, or 88. And so again, we're looking at our abundances. There's going to be way more chlorine 35s. So this is going to be our most abundant dichloromethane isotope. This one will be next because there's still lots of chlorine 35s, and because we've got chlorine 37s here, they're only 24% each. Okay, this is going to be our smallest peak. So largest, smaller, smallest, 84, 86, 88. And that's our pattern that we see there, 84, 86, 88. Okay, we've got now dibromomethane, another example. So again, we can have bromine 79 or 81. We've got 2 79s, a 79 and 81, and an 81, 81. So same idea, right? Molar masses of 181, 183, and 185. But this time our abundance is quite different. Okay, so we've got about a 50-50 mix of each. Okay, so when we look at this, essentially we're going to have the most number of these, right? Because we have 50% of these, 50% of these. So the most amount of options you have, because the bromine here could be switched with the bromine here. So we could actually have these two switched around. It's the same molar mass, but different configuration. So what we see happening is that our 183 peak is actually going to be our largest. We're going to have the most number of dibromomethane molecules where we have one of each bromine 79 and bromine 81. Okay, and then we're less likely to have two bromine 79s or 2 bromine 81s. Lucky last, I'm just going to point out again, this is our ethanoic acid. I just want to point out again our carbon-13 isotope down the bottom here. All right, and to finish off, I just want to talk about combined techniques. So you can use IR, NMR, and mass spec. They're used as separate techniques. You walk to one machine and use one, and then you walk to the other machine and use another. When we're talking about combined techniques, we're talking about coupling qualitative with quantitative analysis. Okay, so you can put a mass spec on the end of a HPLC or a GC. Okay, you can do two-dimensional chromatography, and you can also use the synchrotron. So I just wanted to point this out, that you can actually use them in conjunction with other techniques. But for the purposes of this video, I really want to just focus in on the idea that you can use IR, NMR, and mass spec. They're three different techniques that you can use together to get results from each separately, to then pull your information to find out what your qualitative nature of your molecule is. So that brings us to the end of this long video. I do apologise for the length of this. We've talked about infrared spectroscopy, nuclear magnetic resonance spectroscopy, and mass spectrometry. My name's Amelia McCutcheon from the Zen of Chemistry. Thanks very much for joining me.